We start with the algorithm, and in a 64-bit remainder register, uh, we load it with the dividend at the lower half and upper half 32-bit being 0. That's what the first statement means. Second statement, divisor 64-bit. This is 60 remainder also 64-bit for 32-bit binary division, and divisor is also 64-bit register with upper half loaded as a divisor 32-bit divisor bit pattern, and lower half is loaded with the 32 zeros. And we start with our process. We do remainder equals remainder minus divisor 64. Like, so you can well imagine we need to bring in a 64-bit subtractor in this process. And then we test if remainder is 0, less than 0 or not. If it is not, then we insert 1 into the quotient bit after we left shift the quotient by 1 bit. So we do a quotient left shift to 1 or with a 1. And then we do divisor bit shifted by 1 position towards the right. So we right shift divisor 64 register by 1. Now if my remainder test is negative, it is less than 0, then we first do the rollback, remainder equals remainder plus divisor 64, that quantity that rolls back your remainder, and we just simply left shift the quotient to 1 bit towards the left, assuming the default bit insertion in the register is 0. Okay, that's our assumption, and then we follow through the same step of right shifting divisor register by 1 bit, and then we check if it is a 33rd repetition or not. So for 32-bit operation, we need a 33 iteration in this case. If it is not, then we go back to that step where we are now computing subtraction of the divisor 64-bit pattern from the remainder bit pattern and storing it into the remainder. And we keep on testing the remainder bit and do actions accordingly. So this is the whole algorithm of the binary division in a digital form. Your circuit, basically digital circuit, need to implement this algorithm. The controller of that circuit will do that. Whereas your data path need to have two 64-bit register for remainder and the divisor 64-bit. You need to have a 64-bit subtractor for the main operation, and you have to have a 64-bit adder for the rollback. Okay, so we all know so addition subtraction is the same circuit, so we just deploy one adder subtractor circuit in this case, but it has to be of 64-bit. And your quotient register will be 32-bit with a left shift capability and selectively inserting bit insertion capability at the LSB side. We want to either insert a 0 at the LSB position or 1 at the LSB position depending on the remainder sign, remainder value sign, if it is negative or positive, after we are done with the subtraction of the divisor 64 value from the remainder value. And of course your divisor 64 is a 64-bit register, and it has to have at least the right shift capability by 1 bit. Remainder register doesn't need any shift capability. It's basically you load some value into it. That's it. So how do we construct it now? So we take a divisor register, put the divisor in the upper half of the 64-bit, lower half being 0, and this guy has a shift right capability, and shift right control is coming from the control and testing circuit. And your remainder register is 64-bit again, and it is loaded with the dividend bit pattern, 32-bit pattern, the lower half of the circuit, and it needs to just have a write capability so that controller and test unit can selectively write onto this remainder register. Okay, and the output side of the remainder register is going into the controller so that controller can test its sign if the remainder is negative or positive. It's going into the one of the input of the adder subtractor circuit to make it a remainder equal to remainder minus the divisor bit pattern. And also the dividend part, the lower half at the end of the operation, it will hold the remainder value of this division operation. So this lower half, lower 32 bit is exported out from this circuit towards the outer world, wherever needs that remainder value to be used. This adder subtractor 64-bit circuit has this control of S and A, where if the S and A is 1, it is subtraction. If S and A is set to 0, it is addition. Addition is needed for the rollback, and controller controls that operation code. So first step, it wants to do remainder equal to remainder minus divisor. So it issues a subtraction signal to adder subtractor, and then if this step needs a rollback, this iteration needs a rollback, then controller will issue an S and A equals 0 for that rollback operation, and it issues the right signal to the remainder register at the correct step. And how about the quotient? So quotient is a 32-bit register, left shift capability with selective insertion of 0 and 1 at the LSB side. So that's what is being shown here. Controller issues the shift left control signal, where it also issues some control to determine if a 0 or 1 will be sent into the LSB of the quotient. Okay. So how it does? So let's say this is one simple circuit of AND where we select either 1 or 0. So if load on 0, this signal is 0 and output is 0, right? So we are inserting back quotient as 0 bit. Then if this load on 0 is 1, then AND output is 1. So we'll be inserting back and 1 into the quotient register. Now you might say, why don't we just directly send the load on Z, that control signal, directly to the quotient bit, right? As we say that if load on 0 is 0, we are inserting 0. If load on 0 is 1, we are inserting 1. Why not sending it directly here? Logically, it's okay. We can send that signal. It's okay. Electronically, what I would like to say is that we want to boost up some of the electrical strength so that bits gets clearly into this quotient, and also separate out this controller output from this data crunching part. So all this quotient, divisor, dividend, these are all data crunching part. And as a philosophy of the circuit design, we should not directly use a control signal to be used as a data as well. That's the philosophy of the circuit design. So that's why we introduce a little more extra circuitry here to select between 0 and 1 depending on a control signal. And of course, this controller has a done signal, which then external one knows that, okay, I started this division and when it is done. So after that, they will pick up result quotient from the quotient register and remainder from the lower half of the remainder register.